All right, we're back for more factored form. Hopefully a little shorter today. But I was talking to this hippie the other day, and he's like, "Hey, what do you call my wife?" And I was like, "I don't know." And he's like, "Mississippi." Mississippi, get it? All right. Factored form. We talked about it yesterday. A times x minus the root times x minus the root. We know that the a value tells us whether the graph opens up or down. So if we have a positive a, we know the graph opens up. All right, so it's going to open up, which means will it have a maximum or a minimum? It'll have a minimum. We also know that if we have a negative a, our graph opens down, right? Or sometimes we call that concave down. And if it opens down, that means we have a maximum. So right off the bat, once we look at the a value, we can already know if the graph's going to open up or down, and if we'll have a max or a min. The R1 and R2, they tell us the roots, which are also the solutions, which are also the zeros, or most importantly for graphing, they are also our x-intercepts. So again, we're going to go over three different forms of quadratic equations, and each form tells us some different information. And so the key information we get from factored form is the two roots. All three forms will have the same a value, so all three forms will tell us if the graph opens up or down. But factored form specifically tells us the roots or the x-intercepts. Determine the x-intercepts and direction of opening. Okay, well, we know that a value is positive, which means it'll open up. And if it opens up, hey, here's kind of a cool trick. Look, the u turns into a parabola opening up. It will have a minimum. And then as far as our x-intercepts go, we know they're going to be the opposite of what's in the parentheses. So our x-intercepts will be the opposite of 1/3. So that's going to be negative 1/3. And then we're going to have the opposite of negative 2, which would be positive 2. So those are our two x-intercepts. For the next one, our a value is negative 1. If our a value is negative, we know the graph opens down. You ready for this? I turned up into an up parabola. Let's turn this n into a downward parabola. Look at that, opens down. If it opens down, that means we have a maximum. The other thing factored form is going to tell us is our x-intercepts, which would be the opposite of 8 and the opposite of negative 3. So our x-intercepts are the opposite of 8, which is negative 8, and the opposite of negative 3, which is positive 3. Same thing, our a is negative 2, which means our graph opens down, which means we have a max. And then our x-intercepts, just the opposite of what's in the parentheses. So we're going to have positive 4 and positive 14. Hey, bonus question. If these are our x-intercepts, what's our axis of symmetry? Well, it would be halfway between 4 and 14, which if I want to find halfway, I just find the average. So 4 plus 14 is 18, divided by 2 is 9. The axis of symmetry would be x equals 9. All right, the next one, we have positive 2. So if our a is positive 2, we know the graph will open up, which means we have a minimum. And then we know our x-intercepts will be the opposite of what's in the parentheses. So since this says x plus 16, my first intercept will be negative 16, 0. And then this one says x plus 8, which means our intercept will be negative 8, 0. So today is pretty much reviewing what we did yesterday. Hopefully if you struggled a little bit, this will help you to understand it. And if you think you got yesterday pretty well, hopefully this will make you even better at it. All right, that's really small, so I'm going to read it. Determine the x-intercepts for each function using your graphing calculator, which I already graphed them for us. Then write the function in factored form. All right, so when I graph this, I got x-intercepts of -5, 0, and -15, 0. So when I go to write it in factored form, I know that my parentheses will have the opposite of -15, so plus 15, opposite of -5, so plus 5, and then I need to identify the a value, which the a value is just a -1, so I can just put a negative. So coming up with factored form from a graph is actually pretty simple. Again, another example. My x-intercepts are -6 and -2. So if I want the intercepts to be -6 and -2, I need to make sure that my factored form has the opposite. So +6 and x plus 2. My a value, I look at this one, it's already just 1, so I can leave that as it is because that means there is an a value of 1. Okay, determining another point on the parabola. Let's see if we can do this without the graph first. And in fact, I don't think this will even fit on the graph, so that's interesting. All right, if our axis of symmetry is x equals -4, and we have a point at 0, 6, we know that the other point on the graph that'll have a y value of 6 has to be the same distance from the axis of symmetry. So to go from 0 to -4, I have to go backwards 4. And so if I go backwards 4 more from -4, or find the other x value that's 4 spots away from -4, I'll get -8. So -8, 6 will be on the parabola. Just to kind of show you why that is, if I draw my axis of symmetry there, and I put my point at 0, 6, I know that I'll have another point on the other side of the axis of symmetry. So if I count, that's 1, 2, 3, 4 spots from the axis of symmetry. And if I go 1, 2, 3, 4, that'll give me a point here, which I promised is at -8 for the x and +6 for the y. Those will be equidistant. All right, next one, vertex is at 3, -1, and we have a point at the parabola on 4, 1. Well, I know there's going to be another point on the parabola that also has a y value of 1. And I notice that this x value is 1 spot away from the vertex's x value, which also the x of the vertex is also our axis of symmetry. So if this point is 1 away from the axis of symmetry, that means the symmetric point will also be 1 spot away. So what other number is 1 spot away from 3? That's right, it is 2. So 2, 1. Again, just to prove this, if our vertex is at 3, -1, and then we draw the axis of symmetry that goes straight through that, and then I put the point I was given of 4, 1, I know that to be symmetric, since this is only 1 spot away from the axis of symmetry, I have to have a point on the other side that is also 1 point away. So that would go right there, which is the ordered pair 2, 1. 2, 1. Right? And then my parabola is going to look something like that. All right. Now we're going to kind of do these questions without a graph. All right, so let's see if we can do it. Determine the axis of symmetry, given that the x-intercepts are 1, 0, and 5, 0. Well, we know that these points are symmetric, right, because x-intercepts are on the same line. Or we could just look at the fact that their y values are the same. So we know the axis of symmetry has to be halfway between 1 and 5. So our axis of symmetry is 3. The formula that we used yesterday to do that was just adding the two roots together and then dividing by 2. Right, so 1 plus 5 is 6. 6 divided by 2 is 3. So our axis of symmetry is 3. If we throw decimals in here, it's not any different. It might look a little trickier, but it's really not. So if I want to find the axis of symmetry, I need to find the halfway point between those two x values. So I can add them together and then divide by 2. If I add those together, that's 0.6 divided by 2. And 0.6 divided by 2 is 0.3. So my axis of symmetry is at positive 0.3. If we're given 2 symmetric points instead of 2 intercepts, we actually just follow the exact same process because these x values are going to be the same distance from the axis of symmetry. So we could just ask what is halfway between -7 and 0. If you're not comfortable with doing that in your head, which is -3.5 by the way, you would just add your x's together and divide by 2. So you get -7 divided by 2, which is -3.5. So axis of symmetry always halfway between 2 symmetric points. Determine the location of the vertex. All right, so this actually, I was going to save it for standard form tomorrow. We'll do one example on here today. This is standard form. And if we know the axis of symmetry is -2, we can find the vertex because we know the vertex is always just the x of the axis of symmetry for our x coordinate. And then if we know x, how could we find y? Well, if we know what the x value is, we can plug it in. Plug it in, plug it in. So we plug it in for both x's in the equation. And I would write this out as x squared, so -2 squared, plus 4 times -2 plus 3. -2 squared, -2 times -2 is a positive 4. 4 times -2 is -8, and then we still have plus 3. 4 minus 8 is -4, and -4 plus 3 is -1. So our vertex would be at -2, -1. Same thing on this one. If we want to find the vertex, first thing we need to find is our x coordinate. And the way we can find our x coordinate is by finding the axis of symmetry, which if my x's are at -2 and +2, what is halfway between those? Well, halfway between -2 and +2 is 0. All right. If I know x is 0, how can I find the y of the vertex? Well, I can plug it in, right? So we're going to plug in the 0 for x, and this time we actually only have one x to plug it into. So I'm going to plug it in, and I get 0 squared minus 4. 0 squared is 0, and 0 minus 4 is -4. All right, I'm going to save other problems like this for tomorrow's lesson. We'll get plenty of practice with that tomorrow. We've actually done quite a bit of these as well. All right, we're going to go through some of the key characteristics of the graph again, make sure we're doing okay with this vocabulary, and then after we go through that, make sure we can come up with a factored form for the graph. Domain of every quadratic, all real numbers. Range is always y is greater than or equal to or less than or equal to. And we go to this graph, and the lowest that it goes is right here, which is halfway between -2 and -2.5. So that's going to be -2.25. And we know that every y value on the graph is at that point or above. So every y value is greater than or equal to that -2.5. Our x-intercepts, we just look on the graph. That one's at -1, so -1, 0. And this one is at +2, that's an intercept of 2, 0. Our y-intercept, we just look to see where it crosses the y-axis, which is right here at -2. Our axis of symmetry, we're going to cut straight through the middle here. And I know it's probably a little too small for you to see very well, but this is exactly halfway between 0 and 1. So that's going to be an x value of 0.5. Or, right, I could find halfway between my x-intercepts. So add those together and divide by 2, and you get a half, so 0.5. The vertex is going to be the x from the axis of symmetry, 0.5. And then the y-coordinate is always the same thing we used in our range, so negative 2.25. Interval of increase, does the graph increase for the first half or the second half? Well, if we look at it, it's going up for the second half of the graph. So once we get to this axis of symmetry, which is at 0.5, it will increase forever. So the rest of the graph goes up. The part of the graph that was decreasing was everything on the left of the axis of symmetry. So the x value, as far as we can go, the x value here will be negative infinity. And as we go this way, the graph continues to go down until we get to the x value of 0.5. So negative infinity to 0.5. Hopefully with the interval of increase and decrease, you're starting to recognize that it's always a positive and a negative infinity somewhere in there. And then the number that you use is always your axis of symmetry. So there are some patterns you can identify. Oh, I forgot the most important part, the factored form. So to make sure we can write this in factored form, first thing I need to put is my a value, which my a value was just 1, so I don't need to write it down. And then for our factors, we're going to put the opposite of our x-intercepts. So if my intercept is negative 1, this will say x plus 1. And if my other intercept is positive 2, my factor will say x minus 2, right? Factored form. Last example like this, domain, always all real numbers. Range, this is actually, I've got a nice little decimal here, that's negative 0.25. And our graph is above that, so y is greater than or equal to negative 0.25. Our x-intercepts are right here at positive 1 and positive 2. Which, let's go ahead and skip to this one. If our intercepts are 1 and 2, where's our axis of symmetry? Well, it has to be halfway between those, right? So halfway between 1 and 2 is 1.5. The y-intercept, I just look at the graph, it's at positive 2, which some of you might be starting to notice that the c value is our y-intercept. That's tomorrow's lesson. So our y-intercept is 0, 2. The vertex is always the x of our axis of symmetry and the value from our range. Or you can just look at the graph. Right? That point right there is 1.5 and negative 0.25. Interval of increase. Well, if I go to my axis of symmetry, which side of that is the graph increasing on? It's increasing to the right of it. So we're increasing from our axis of symmetry until forever, which means the half of the graph that decreased was the first half of the graph. So from negative infinity until 1.5. Going back to our factored form, it's going to be f of x equals, my a value is 1, so I don't need to put anything. My first intercept was a positive 1, so this needs to say opposite, x minus 1. And then my second intercept was positive 2, so this will say x minus 2. Factored form. All right, a group of students each write a quadratic function in factored form to represent a parabola that opens downward and has zeros at 4 and negative 1. Well, in order for it to open downward, what has to happen? Our a value has to be a negative. So that is good. This one also good. This one bad, because positive 2 would open up. So Tim, he's wrong. Now this one does have a negative which would open down, but Michael still got a thumbs down. So that must mean that Michael didn't have zeros at 4 and negative 1. So let's take a look. If Michael puts 4 and negative 1, what will the actual intercepts be? Well, if this is x plus 4, the intercept will be the opposite, right? So instead of plus 4, it'll be negative 4. And instead of minus 1, this will be positive 1. So when Michael wrote his function, did he really have intercepts at 4 and negative 1? Or did he put intercepts of negative 4 and positive 1? Michael, you almost had it, but you made a mistake, which we all do. It's okay. Hopefully he'll learn from it. But if we want our zeros to be positive 4, the factor needs to have negative 4, right? So negative 4, negative 4. And if we want our other 0 or x-intercept to be negative 1, then our factor has to be the opposite. So x plus 1, x plus 1. So nice job, Maureen and Tom. All right. Use the given information to write a function in factored form, sketch a graph, and label key points. We're not going to do all these key points yet. We'll do those tomorrow. But again, if we want our parabola to open downward, what has to be in front? Well, if we want it to open down, we have to have a negative a value. I'm going to pick negative 3. Doesn't matter what number you put there. If it's negative, it'll open down. But if our zeros are going to be at 0 and 5, 0 and 5, in order to have 0, that would be x minus 0. But what's x minus 0? It's just x, right? So anytime it's just an x, that means one of our intercepts will be 0. And then to get one at positive 5, we need x minus 5. So our graph will look something like that. On this next example, we want it to open up. So if I want it to open up, I need to have a positive a, which I'm just going to leave this one as 1. And then if I want my intercepts to be at negative 2.5 and positive 4.3, I need to make sure that my factor is the opposite. So for negative 2.5, I'm going to put x plus 2.5. And for positive 4.3, I'll do x minus 4.3. So this function will give us a graph with these x-intercepts. And because the a is positive, it will open up. So it'll look something kind of like that. All right. Given a parabola that opens downward and has zeros at negative 2 and 3, represent it as a quadratic equation in factored form. Okay, well, if I want it in factored form, I'm going to go right here. If I want it to open downward, I need a negative. And then if I want my zeros to be at negative 2 and positive 3, I need to make sure that my factors are the opposite. So for negative 2, I need x plus 2. And for positive 3, I need x minus 3. The graph would look something like this. I'm not going to worry about the y-intercept today, but I would expect us at this point to be able to find the axis of symmetry. If we know that the roots, or zeros, or intercepts are at negative 2 and 3, I know that the axis of symmetry has to be halfway in between. So halfway in between negative 2 and 3 is going to be a negative 1/2. Positive 1/2. Excuse me, negative 2 plus 3 is positive 1. Positive 1/2. All right. Summary of the key points. So, factored form of a quadratic. We talked a lot about parabolas. We talked a lot about quadratics. At the end of the day, what we really want to make sure that you know is if it's in factored form, what do we know if the a is positive? Well, if a is positive, it opens up. And if a graph opens up, where is our vertex? It's at the bottom, which means we have a minimum. If a is, if a is negative, that means our graph will open down. And if our graph opens down, that means we have a maximum. So anytime you see something in factored form, we expect you to be able to look at the A and know if the graph opens up or down, or if it has a minimum or maximum. More importantly, however, from factored form is knowing what R1 and R2 represent. And R1 and R2 are the roots, which are the solutions to the problem, which are the numbers we can plug in to make the equation go to 0. And I would say most importantly, they are our x-intercepts. And we know it'll always be the opposite of what's in here. So if we have f of x equals x plus 2 times x minus 9, what would our two x-intercepts be? The x-intercepts are just the opposites, right? So instead of positive 2, our x-intercept will be negative 2, comma 0. And instead of minus 9, our other x-intercept would be positive 9, comma 0. All right, another one down. We'll see you tomorrow for some standard form.